Greetings again. This is our video class for the second half of, I guess, what I call week 12 subject matter, which in this case would just be sign multiplication, Wallace multipliers, and Karatsuba-Ofman multiplication method. So we kind of covered this in class last week. We talked about sign multiplication basically as a method of simplifying or perhaps accurately obtaining a product when we view the operands as signed numbers. Just like as in addition, two's complement addition and subtraction, we need to worry about the product being correct in terms of its representation. And we still assume that these operands in our multiplications are represented in two's complement notation. So when we multiply them, we need to make sure that the product has the correct two's complement representation. So typically we have two operands, which we've been assuming so far, u and v. And then with respect to one another, they could actually assume these four combinations. They could both be greater or equal to 0. The multiplicand could be greater or equal to 0. Multiplier could be less than 0, or the other way around, or they could both be negative. And so, and on top of this, we have the multiplicand to have n bits and the multiplier to have m bits. This is what we assume. And so the result will have to be an m plus n bit product. And of course now we're assuming that that these two operands by these representations we pick here can actually be positive or negative. So when the two operands are both positive, the m plus n bit product basically represents a proper product. And this I explained in class by simply saying that when you take these two operands, u in n bits and then v in m bits, and then assume that these two operands are both positive, then their leading bits must be 0. And so when you multiply two such numbers where the leading bits are 0, then you would actually end up having a product that would not be able to penetrate into the upper half of m plus n bit numbers, all of which will have to begin with 1. So effectively, because you are having two operands in this case with leading bits of 0, and that simply means that you would be a number between 0 and 2n minus 1 minus 1, and then v likewise be a number between 0 and 2 to the m minus 1 minus 1. And if you multiply those two numbers, then you're going to get something that's going to be less than 2 to the m plus n minus 1 in the exponent, and that would just keep it within the positive range of these products that we have to kind of like assume will be divided into two halves, the lower half of which will be positive numbers and the upper half of which will be negative numbers. So in this case, effectively what we're saying is that there's no possibility of any erroneous product. You just take these two numbers with leading bits of 0 and multiply them. You'll get a proper product. Don't have to worry about whether you actually ended up having a wrong sign-wise product to yourself or for yourself. So no correction is needed. Now, this second case requires a little bit of attention because our second operand here, which is our multiplier, is actually negative. So when this is negative, then we need to assume that negative multiplier has this kind of a representation because it's a two's complement number. Its modulus is m, so it's 2 to the m minus absolute value of v. And then now this is what we're multiplying. So when we multiply this, a positive number multiplied by a negative number, we are supposed to get a negative product. So whatever this is, it's going to have to be converted into something like 2 raised to m plus n minus u times the absolute value v. Now instead of having that, we basically get this expression here, because if you just multiply this out, that's the first term here, and the second term is going to be this times this. Now that is going to have to be converted into, like I said, 2 to the m plus n minus u times v. And for that to happen, we need to basically add to this term here, which is 2 to the m plus n minus u times 2 to the m. So this minus u times 2 to the m will cancel with this, and then this will of course be added in, so you get the correct form. So a correction is required, and the correction is basically equal to this. This is just another way of actually saying what this is, because in m plus n bits, this is just, I guess you can say, congruent to minus u times 2 to the m. And this is symmetrical, so I'm not going to mention, not going to talk about this. You just have to correct, but correction is on the u side as opposed to v side. Because u being negative here is what impacts the answer ultimately. And when both of them are negative, now you expect to get a positive product. So in this case, our two operands now have these two's complement representations, so that's what you're effectively multiplying. When you multiply these two numbers, you then get this product here, this result here, and basically this times this is going to be plus u times v in absolute value, and then the other two terms come up from the multiplications of these terms, and then there is another term which is not shown here because it's 2 to the n plus m. That has to be outside of the 2 to the n, the modulus of this whole product, which is 2 to the n plus m. And so that term kind of like does not appear here, and that's for a good reason, because that's actually beyond the product range that we could actually produce here. Keep in mind that all of our numbers will be between 0 and 2 to the m plus n minus 1. So this 2 to the m times 2 to the n would just simply be a number outside that range, therefore we could ignore that. So this is what you get, but the real result you want to have is u times v in absolute value. That means you really, to get that, you have to sort of like add this term into the result that you have. So without extending either of the operands in sign, and the sign extension will be obvious to you in just a little bit, these are the corrections we require. Some simple examples are provided here. There's one example. In fact, we'll have more examples down the road, but in this situation, we are looking at m and n being equal to 3 quickly. So if u is equal to minus 4 and v is equal to 3, we simply are in this situation here, in the third row case. And so when we multiply, we're basically multiplying, and we have this multiplication, which is what this is. So if you just substitute all the values in here, ultimately you get 52. Now this is the case where you need a correction to be made, and the correction that is required is basically going to be processed by adding this quantity here, which was this correction that we talked about, 2 to the 6 minus v times 2 to the n. So since v is equal to 3, and 2 to the n in this case 2 to the 3, so that's the correction portion, and this is the actual thing that you generate by way of multiplication. At the end of the correction you get 52, which is actually equal to minus 12 in 6 bits, and that's what you wanted to get because you multiplied minus 4 by 3. So the next example is similar. Correction may be a little different because we have two negative numbers, so the correction will have to be different, but the idea is there. So the correction step is required in, as you can see, 3 of the 4 cases here. Only in the positive operand instance we don't need to correct anything. So with that stated, let's just look at the case when we extend one of the two operands. We could actually do this for the multiplier as well. They're very symmetrical in this representation because we're not really too worried about the exact order of the multiplication here. We're not looking at the actual hardware implementation, but we're looking at symbolically, algebraically, what results, and what we would be able to obtain by just simply multiplying these representations. So the first row, again, don't need to make any correction. The second case, u greater than 0, v less than 0. So what you can see here is that we're just simply, again, multiplying, but multiplicand is sign extended, but with zeros, with u being greater than 0, that sign extension would just not change the value of u, because it'll still be u itself. A sign extension here, by the way, means that we're going to be putting zeros on the left hand side of the representation. So with zeros padded on the left of the most significant bit of u will not change its value. That's why you see that u remains put here. So in that case, this is exactly how we had it before in the earlier slide, and so we still need to do a correction. The change happens when, in fact, we look into u less than 0 case. Now, when we sign extend u, the sign extension would ultimately amount to writing u as 2 to the m plus n minus u, because that's what happens when you sign extend an n-bit number into m plus n-bit number. U itself is an n-bit number, and now we're going to make it an m plus n-bit number as a negative number. When we sign extend, we pad ones in front of this number. Ultimately, all that means is that we're actually now, instead of like calling it 2 to the n minus u, we are now calling it 2 to the m plus n minus u. That's how this sign extension works. You could actually try this out to convince yourself that's what happens. It's fairly straightforward. So with that correction made, now look what happens. When we multiply this by v, we're supposed to get, in the end, basically u times v, absolute value of u times v. Now we get 2 to the m plus n times v minus u times an absolute value times v. So because 2 to the m plus n times v is going to give us something that is either 0 because v itself is 0, or v is greater than 0, such as 1 or 2 or 3, some number that's greater than 0, then this expression here is going to amount to some multiple of 2 to the m plus n, which in mod 2 to the m plus n is equal to 0. So therefore, there's no need to make any correction because we got ourselves the product we needed here. This just simply gets wiped out. In the fourth case, even though we sign extend u, we don't sign extend v. In the end, when you complete the multiplication, this times this term, which is basically 2 to the m plus n times 2 to the m, will be outside of our range, so we don't have to worry about that. But there is a term that's going to have to come up through this minus u times 2 to the m, which we have to account for. That the last term will be the product that we're interested in, which is u times v in absolute value, which is this product here. But we also get ourselves a minus a u in absolute value times 2 to the m, which sort of like still sticks out here. Therefore, this has to be fixed, and we want this to be a positive quantity, which is u times v. That means we have to add this quantity back in. And that's what this term is all about. So here's again an example where u and v are set to minus 4. And with a sign extension of u, this is in fact where the correction is not required. We're going to basically write this u as 2 to the 6 minus 4 as opposed to 2 to the 3 minus 4, which is what we've done over here. And now we go to the multiplication. So when we do make the multiplication, we basically get ourselves this quantity, which is nothing but equal to 52. This is just 64 minus 4, which is 60 times 3. And you know, if you just look at the mod 64 of that, this is 180, and then just subtract from that 128, and that gives you 52. So, and of course that itself is a minus 12 in 6 bits, and that's what we should have gotten. And no correction was required. We simply sign extended the multiplicand, and then that automatically gave us the product. All right. So this idea, and here's another example of it, but I'm going to skip because these will be in the lecture notes as well, so you should be able to follow these. And another example here. So I'm going to skip over these because, like I said, these are fairly straightforward examples. And the final cases, I guess, is the u being greater than being greater than 0, and then v being negative. That would have been this case, and there's still a correction required. So only 2 of the 4 cases you can avoid correction. Now, it is possible to really conduct all these operations in binary, and so you can see that the sign extension of 4 just inserts 3 more 1s in front of it here, and that's how you do the multiplication. And when you do, you just, out of the multiplication itself, you get the result directly, as you would be just obtaining it. In the positive case, again, there's no issue of overflow. You get the answer right away. And in the other 2 cases, corrections are required, and the corrections amount to what we computed, which in this case, I guess, happens to be 32 in both these examples. So this just illustrates how sign multiplication is handled. Now, it's possible to avoid the correction altogether, and all you have to do is just simply sign extend not only the multiplicand but also the multiplier. When you do, then you don't really have to worry about any correction, because you're ultimately bringing the operands into the full width of the product, and intuitively it should make sense to you that you don't need to make any corrections because you already sign extended the 2 operands. Of course, the penalty that you pay for that is that you now have larger circuits to deal with, and this is why people don't really go full force on the sign extension and try to do this in a more moderate, in moderation, and just not rush to sign extend things because we might have incorrect results. If anything, they actually try to avoid even sign extension of either operand, but do it implicitly, as we may actually see that. This is just a further justification as to why this really works, when you sign extend both operands. And so you could just look at these algebraically yourself to figure out that this is indeed the case. So this is just a table which shows that when you sign extend both of these things, you ultimately get the correct answer. In this case, of course, the answer will be u times v, which it does get to be that way because with the sign extension, both the product of 2 to the n plus n times v and the product of u with 2 to the n plus n, they will be outside of our 2 to the n plus n range, and therefore they will not be in the mix. Of course, 2 to the n plus n times 2 to the n plus n itself will be outside, and then what survives this whole process is u times v, which is basically what this is. So this alone shows you that in this particular case, there's no need to worry about correction. The other cases you can argue, of course, the first case is trivial. These 2 cases you can again examine to see why this happens. All you have to do is to pay attention to, as we already done this in the case of sign extending u and not v, even that we did not need a correction. I guess in this case we did not need a correction. So with the v being sign extended, of course, or u on the other side of it, you would not need any correction. So that's just that, and of course this is for the justification for that. And this is a little circuit here which sort of takes care of sign extended multiplication algorithm in hardware, if you like. So so you can see that we have a partial product register, and we then have a n plus n bit register into which we put our multiplicand with n bits coming from here, and then the sign extension basically taking place here, where the number is sign extended, as we would do it because that's what we said. We will sign extend the multiplicand. So if it's a negative multiplicand, you're going to pack this with 1s. If it's a positive multiplicand, you're going to pack these with these flip-flops here with 0s. And then you have this n-bit multiplier, which will come in, and based on the bits of this n-bit multiplier, you have this control circuit here that's going to just perform the multiplication. And then, of course, the correction will have to be added in, which is what this circuit does, based on the ultimate pattern that we have to pay attention to. That is to say, in the case that V itself is negative, and we are in this step, some correction is required. So this is like the correction step. Basically, this is what is written here. If u is greater than 0 and v is less than 0, t is equal to u. If u is less than 0 and v itself is less than 0 as well, then you have to make this correction, which is basically what this circuit ultimately accomplishes. So you set that t is equal to this, and those are the sort of corrections that you have to basically perform in this situation. So this circuit just simply simulates what we said we would do in the case that we sign extend I guess any one of these tables will do, and we sign extend the multiplicand, but then we don't sign extend the multiplier. It's just a circuit which accomplishes that, so that I think you should just look at that as such and analyze it from that point of view. And I also talked about this in class. This is what's called implicit sign extension. So this is a little tricky. This is somewhat similar to multiplying two unsigned operands. But here we have to worry about the sign. And so when we talked about the sign, I mentioned the fact that we are sign extending the multiplicand, which is basically the term that we're adding here based on the multiplier bits. This assumes that the bits that are not shown here are all ones. In the event that V, the current bit that we're multiplying this, ending this multiplicand's bits here, these happen to be 1. Of course, if it's 0, then the leading bits will also be 0. So in other words, if this acts as a negative number, the sign bits will all be negative, which is to say, well, they will all be 1s. So so ultimately, what we need to do here is to figure out exactly what kind of a bit will be computed when we add these numbers together. So initially, for example, partial product is 0 with leading bits of 0. So there is a hidden 0 here, and for this particular operand, multiplicand, that is sign extended, there's a 1 in here. So there's a 0, there's a 1 in there. And so what we're doing, basically, we're adding these two bits and generating a carry out of this particular pair of bits, and that carry plus this bit, which is in this case 0, plus this bit, which is in this case is equal to 1, is going to determine what this is going to be. So since the carry out is equal to 0 here, because we're adding 0 to 1, this bit is 0, which is not shown, and this bit is 1, which is also not shown. 1 plus 0 is going to give you this 1 here, and that 1 gets shifted in as we actually shift our partial product to the right. We learned this technique earlier on in the first part of this video lecture. I talked about shifting the partial product to right is the same as shifting the multiplicand to the left. So this is what's going to happen. We're going to keep the product basically stay within the n bits of the partial product register, and then the n bits of the multiplier register. Since we have n plus n bits to represent our product, the concatenation of these two registers will actually be enough to represent all of our n plus n bits, or hold them in our basic memory structure here. So this is how you get to compute these bits. Now in the next round, for example, you have this 1 over here, and you have a 1 over there, so that's going to be generating a carry, if you like. So that carry gets generated here and comes in. Now this time we have actually 1 in here because this is a partial product that needs to be sign extended, and then this is also equal to 1 because we're still having a 1 1 1 a 1 1 0 0 pattern, because the second bit of our multiplier is still 1, as you can see. So we have a 1 in there and a 1 in there, and then a 1 carry comes in. So 1 plus 1 plus 1, that is 1, the carry, plus 1, plus 1. Again, these are invisible bits, but you can surmise them by the sign extension formula that in fact is down here, which is to extend this by sign, extend this by sign. So 3 ones add up to 3 with a carry of 1, which is how this gets generated, and then it kind of gets pushed in. So the same process repeats over and over again until we finish this multiplication, which in this case should give us basically 3 times minus 4, and that is going to be basically minus 12, which is what this number should be if you just take the complementary bits and add a 1. That's what you should get. So in general, this is the formula that really represents this operation that I mentioned to you. And what you notice here is that we only have to look at the bit past the leftmost bits of the 2 operands we're adding here, namely the partial product and the multiplicand, which is basically kept in the same place, but the partial product, of course, gets shifted to the right, which is the same as like shifting the multiplicand to the left. And this formula is exactly what I told you would be happening. This is the carry that comes out of the significant position, most significant. This is exclusive ORed with the extended sign bit of, this is like the iteration, K is just the iteration number, and it's most significant bit of this partial product, which is what we sign extended with, and also the most significant bit of U, which is our multiplicand, sign extended, of course, after it's ended with VK. So for example, when this is equal to 0, the multiplier bit, then the bit extension here is going to generate a 0 because this is actually 0 at this point in time. When we sign extend it, that's going to be 0. So that 0 will come in here. And this, of course, is going to be a 1 right here, partial product. And the summation of the 2 bits will give you a carry of 0. Again, you have a 0 and a 1 and a 0, and that's the carry of 1 here. That's how you generate this 1 when we actually look at this bit here. That bit multiplied with U, which is all zeros now, because this is not all 0, but ending it with this bit is going to make it all 0, and then the carry out of this addition is going to be just 0, and then the extension of this pattern is going to give you a 1. So 0 carry coming with a 1 and a 0 here for the sign extension of the extended U multiplied or ended with V2. That means, iteration number 3. This is like K equals 0, K equals 1, K equals 2, K equals 3. This is how we go about doing this computation. So this expression basically is going to compute for us these bits that we need to have. They seem to be invisible here, but they really are computed out of this formula to be able to stick these carries back in. So I guess this is somewhat more detail and tells you what happens in each of these iteration levels, if you like. And it's but the same idea. This is just like how I explained before. And here's perhaps a a situation or a representation where we could see how sign extension works. Like if the initial partial product is 0, sign extension will make it like this. And this was our initial multiplicand, and sign extension will make it like this. And so the addition basically generates these carries the way that is indicated here. The red ones are the ones that are basically shifted in, and in reality we have all these bits, but we only need to look at the leftmost bit, or the bit immediately following the leading bits of the 2 operands, the partial product and the multiplicand. Of course, the purpose of all of this is to keep the addition itself to only n bits. As you notice that all we're doing here is just add n bits at a time. So we are still using an n-bit adder to do our multiplication. So there is sign extension, but the sign extension is done only implicitly. That's why it's called implicit sign extension. I hope this discussion has made it clear enough to you, so that you could actually look at this a little more carefully when you go over this video yourself. All right. So now let's talk about array multiplication a little bit. So array multiplication simply means instead of like shifting in time, we're going to basically proceed with the iteration of the multiplication process. We're going to do this in space. So you can see that that these columns that you see here is a column and a column and a column. Every column has a name like column 5, 4, 3, 2, 1, 0. These columns basically represent the products of multiplicand and multiplier bits, where the column index is the sum of the indices of the multiplicand and the multiplier bits. So in other words, like it's 1 and 1, or 0 or 2, 0 and 2. They add up to column 2, the index. Here, this is like the second bit. When I say second, really meant third. It's just index-wise 2. Everything begins with a 0 in this representation. So, like U2 is the third bit from the right, and V1 is the first bit from the right. And so 2 plus 1 is equal to 3, and that makes column 3. Every one of these numbers, like U3 V0, U2 V1, they add up. The indices add up to 3. Here they add up to 4. And here they add up to 5. Now, because U itself is a 3-bit number, is a 4-bit number, and V itself is a 3-bit number, we don't get U3 and V3. That's where everything ends right here. So these are full adders. As you can see, they have their carriers coming in. And as you notice that the way that the structure is sort of indicated here, we can maybe say that the diagonal paths are the carries, and the operands, the products that really constitute the product of the multiplicand and multiplier bits, come in as one of the two bits to each of these full adders. And of course the carries initialize to 0, but after that the carries that are generated from these columns, like these columns, will have to go to the next place. And then the carries that get generated from this particular column must move to the next place. And because we feed a 0 here, the carry kind of travels down to this particular place. This is where actually convergence of results begin to happen. If you think about this for a second, in each of these cases, like including this and this, we had these adders basically generate a multitude of carries, like 1 and 2, and in fact even this one having a carry. But at this point in time, we can just simply combine this. There's nothing else that's coming like this particular pair, and we can take this bit and then just push it into this place. So the fact that no new operands will have to be product of these U and V bits will be needed at this point in time. Because we expire them here. Then we can just simply shift them to the right, to the left here. This is where all of our bits have been multiplied already. We began there, and then we ended here. So there's no more these product of bits. So that's how the left shift begins here. This is this is what terminates the I guess the height of this array here. So just doing this, ultimately you multiply a 4-bit number by a 3-bit number, and you're supposed to get a 7-bit product, which you have if you just simply look at these bits, like it's P0, P1, P2, P3, P4, P5, and P6. A total of 7 bits is generated. So what happens from, we could start from this very principle and then arrive at Wallace multiplication. So what Wallace basically saw in this process was that we had these bins that correspond to these columns, and all we had to do was to simply add these bits in the same inside the same bin to generate effectively 2 bits out of each. You kind of see that happening, like here, 2 bits there, 2 bits there, 3 things come in and 2 bits could come out. So instead of basically using full adders like this, he converted them into what he called carry save adders. And so look at these as basically numbers, 2-bit numbers with a carry save notation. So effectively, you have this trapezoidal shape here, where this given column, for example, has all the products of bits that are in the same weight position, like I plus j or n plus m minus 2, etc. And you can just take 3 of these at a time and produce 2 things out of each. And where the leftmost of the left bit of this 2-bit representation in each of these terms that you're going to generate in this area, for example, shifting to the left, and then the other one is basically moving down. Of course, it'll then be united with or joined with other such terms, and that will just make this computation proceed to the end. And then ultimately he puts a big adder at the very end to complete the addition. So let's look at an example. So here's a Wallace multiplier with a 6-bit operand, a multiplicand, and I guess a 4-bit multiplier. Again, we starting out with the first row here. You can see that we take V0 and multiply it with all of U bits. We take V1 and then multiply it with, by multiplication I really mean ending, because these are just bits, with all of the bits of U. And likewise, everything is done here. So these terms that we now have collected are basically, they have the same weight, and therefore we can give them such significance, like this will be 0, this will be 1, 2, 3, 4, 5, 6, 7, 8. We got these positions. So what we do is we just bring the 0 down. There's not much we can do about it because it cannot be paired with anything. But these two can be paired together. When they get paired like this, they are in the position, both of them are in the first position let's call that position 1, not first position, but position 1. So we have 1 and 1, but when we add them, we get 2 and 1, because 1 will be like the carry. The 2 signifies the fact that it has to be moved over to the next column. When we take 3 of these together, like this, we have 2, 2, 2, and then we have 3, 2. Because one of them will have to go to the third, and the rest of it will be within this column. Now, while we're doing this with this 2, 2, 2, 2 combination, we're also doing it with these 3 combinations, but there are 4 of these. So what that means is that we can only take 3 of them at a time, because we only use 3 by 2 carry save adders. So 3 are combined together. That 1 stays there, and it has to be dealt with somehow. But now when we take these 3s that are actually painted red here, then we get 4 and 3. So we have 3 and 3 left that needs to be dealt with. So this whole process is really, basically combining, which is like, a carry save process, and after which we collect things and align them again. So what you can see here happening, if we just go over this 4 again the same way, and 5 the same way, once we finish this addition process, we pick ourselves these 3 terms at a time, 3 terms at a time, 3 terms at a time, 3 terms, and then 2 terms at a time, because there's no third term here, and 8 just travels down. We then move all those terms that are actually outside of their column, like 4, like 5, like 6, like 7, to the next place, like 8. So when we do this, we have a new reality here. We began with some 1, 2, 3, count them up, some number of terms, but because we took 3 things and then combined them into 2 things, we certainly shrunk the number of terms from here to here in a logarithmic way, which will be not base 2 but base 3 over 2, which will be like 1.5. So you can see what happened here. We just simply made this shift, and then in the end we got some more terms with 3 patterns or 3 combinations, and they have to be combined. Now, by the time you combine these, like here, we get 5, 5, 5, we get 6, 5, and so on. The whole process ends when everything is actually down to a pair. Until then, we have to continue this process. The reason that we stop when everything is a pair, like here, and these terms actually are just skipped over because we kept them in these 2 levels. Nothing changes there. Now that we got them into a pair in every one of these, that means these terms are just basically just copied over this way. It is this last row that matters. You can view this as basically some coding of a product in terms of two numbers that still have to be added together. And that is, the first number is going to be this number here, 9, 8, 7, 6, 5, 4, 3, 2, and then 1. I mean position-wise, if you like, and 0. Okay, there's a 1 in there which we just don't really show here. If you think about this also as a 2-bit pattern, it's like 1 and 0. So we grab 9, 8, 7, 6, 5, 4, 3, 2, and 1, and 0, and make a number. And then second number that we're interested in here would be like this number, 8. That means its leading bit will be 0. 8, 7, 6, 5, 4. These are the bits of our second operand. So we really have a pair notation that represents a product by way of having these two, I guess you can call them n plus m bit operands, now that we've created them, and we need to add them together. So that addition happens here. This first portion of the circuit diagram that you see here is actually this just to get these pairs. You can see, for example, we put U1 V0 U0 V1 into this full adder, which would be just this particular column, and then the next column, for example, is going to take 3 things and then produce 2 things out of it. And 0 was this particular column here. Okay, so what happens in the end that we get these bit positions. You get the black digits and then the red digits. So the black digits come together and make a number, like an operand. And where the zeros are added here because we didn't have these numbers for the first one, like 9, 8, 7, 6, 5, 4, 3, 2, and we needed 2 more bits of 0, and that's what these zeros correspond to. This leading bit of 0 comes out of the fact that this second number begins with 8. There's no 9 here, and that's where that 0 appears here. So you can see how we just form this adder now, which really has an m plus n bit operand on the left and an m plus n bit operand on the right. And this is our basically Brandt and Kung adder. So the point is that the decimation of the number of terms here, which would be, of course, m times n, because when you multiply an n-bit number by an m-bit number, you're going to have m times n such product terms. Like all these things, when you add them up, in this case, they must actually add up to 6 times 4, which will be 24. There must be 24 of these terms in here somewhere, all of them combined together. What we're doing, we're taking 3 of them and making 2 out of them. So there is a decimation or a compression. This compression is going to ultimately bring it down to, as in this case, a number of terms which is equal to, I guess, 18. Or is it 18 or 20? Let's see. It's actually 9 bits. So it's 18. So we went from 24 down to 18 because it's 2, 4, 6, 8, 10, 12, 14, 16, 18 because we put these dummy inputs as well. Because in one case we didn't really have a leading bit, as you notice here. There was a leading bit of 0, but we don't really need that bit. So you could see that this whole process is a stage of decimation of the total number of product terms we have to generate when we multiply an n-bit operand by an m-bit multiplier, followed by this one big adder, which is really not that big after all. It's m plus n-bit adder, and its complexity, in terms of its hardware complexity, it's going to be order n plus m, and the depth of this will be order log n plus m. So that is still order log n if m is of order n. And so that doesn't really make it any more complex. But the complication is going to come here. Now we know that because we're taking 3 things in and producing 2 things at a time, that in the end, the number of levels that we're going to travel through will be logarithmic. This really is the idea that began this whole process of computing things in a logarithmic depth um, space, if you like, instead of like having linear growth with, in terms of, if you just think about the prior algorithms, they all require m iterations, but now all of a sudden this is going to bring us down to basically log, not base 2 but base 3 over 2 m plus n steps, and that is a considerable reduction. Again, if m is the same as n, for example, you're talking about log 2n, that is 2 times n. That's just 1 plus log n. That's not a big deal. So this formula basically just articulates it somehow, that this is the kind of time of taking m times n objects. These are the bits in our product, but the operand multiple products, the bitwise, the n gate outputs, if you like, which I did not show them in here, but these product operations are just like n gates here. And so we take mn of those, and then we shrink them down to 2 times mn over 3. There's certainly a reduction, and plus some tau a being just going through these full adders or carry save adders. Carry save adders basically are like full adders where the carry input is considered to be just one of the 3 operands, as opposed to a separate or separately labeled carry input. And then we just have carry out and a sum output. So if you just reduce this, like I said, it's going to be something in the order of log 3 over mn as opposed to 2 over mn. 2 log base 2, that is mn, but this is still a logarithmic reduction. It is possible to actually make the reduction somewhat more aggressive by taking things that would actually reduce things. For example, if you, instead of like taking 3 bits, if you took 4 bits, then with 4 bits you can represent I'm sorry, with 4 inputs rather. 4 inputs can be, for example, represented by, let's see, 3 inputs, but 5 inputs can also be represented with 3 inputs, and 5, 6 as well, so you can make it 7 by 3, because you can go up to 7 inputs and you could still represent them by 3 outputs. With 3 outputs, you could actually just express a number between 0 and 7, and since you would be receiving up to 7 inputs, each of which will be either 0 or 1, if I could draw this box in here somewhere, you could just imagine that. Okay, 7 wires coming in with 3 wires coming out. In each of those wires you can have 0 or 1, so you could actually have up to 7 here, and 3 bits will suffice. So that would be a 7 by 3 reduction. Excuse me. My cough is still with me a little bit, not much, but when I talk too much, it kind of comes back. But anyway, going back to this, so you could actually make this compression a little better then. It could be like 7 over 4 as opposed to 3 over 2. 7 over 4 is pretty close to 8 over 4, which would be like 2. And that's pretty close to 2. So so the Wallace time, multiplier time, would be somewhat in the order of log mn, which is log mn. I mean, like I said, actually, I said that n it is not m plus n. It's m times n, because the number of product terms we have to assemble would be m times n. And so I stand corrected. It's m times n, just obvious reason. It would be that we have m bits of multiplier and n bits in our multiplicand. So every bit has to be ended together with every bit in the other operand. So that's m times n. And so that's log 3 over 2 mn. But even if m is equal to n, that will be n squared, be 2 times log n. So it's just like not 1 plus log n, but 2 times log n, still log n order-wise. So the only other thing that remains to discuss, I think, in this portion is Karatsuba-Ofman multiplier. And so the trick that these 2 Russian researchers actually discovered was that you can, and this is sort of like a little bit of a backing up from what we already accomplished. We should not really overlook what Wallace accomplished here, which is very important. So the The order of presentation here does not mean that this particular result that I'm talking about is actually any stronger. It is just a different way of multiplying things, and this could be done algorithmically a little more effectively maybe than the Wallace multipliers. Wallace multipliers were basically driven by, I guess, electrical engineering concepts, more like a hardware idea, and whereas Karatsuba-Ofman is dealing with more of an operational or a sort of mathematical representation of multiplication, which in this case is like this. If you take our two operands, u and v, and these are two n-bit numbers. Now I'm just basically leaving out m and n, just making that sure that I could be simplified so we can follow this. So u itself is going to be basically some n-bit number multiplied by 2 to the n, and another n-bit number, and these are the upper and the lower half of the two n-bit numbers, 2 n-bits of this operand u. So the upper half, of course, of n-bit numbers will have to be shifted by n bits. That's what this does, and then the lower bits are here. Same is true for a v. Now, when you multiply these two numbers, what you get to see is that you get basically 1, 2, let's say 2, 3, and 4 products, each of which will be half the size of the original multiplication because these are half size, like UH is an n-bit number as opposed to 2 n-bit numbers. So here is a product of 2 n-bit numbers, a product of 2 n-bit numbers, a product of 2 n-bit numbers, and product. So there are basically a product of two n-bit numbers has been reduced to product of 4 n-bit numbers, and that is the recursion, or that's a divide and conquer idea. So if you were to write this as some time function, you will be writing t2n equals 4tn plus whatever time it takes to add these things, which will probably be, if you do this sequentially, order n, or if you do it by Brandt and Kuhn, it will be order log n. The point that they actually were able to discover was you don't really have to do 4 multiplications, but you can just get away with 3. And that's because they were able to write this product, which is this expression, as in this form. As you can see, what they did is they kept this one as it was, but then they changed this middle term. All they did was they multiplied UH plus UL by VL plus VH. That's their second multiplication. And then they realized that that's going to generate some of the terms that they desire, like UH and VL will be desirable, and UL and VH, because we need those terms, and UL and VH will be desirable. And they want to have UH and VH. They do, because they have to have that term. But what they also had to do is to get rid of this term, UH times VL times 2 to the n, because that's an extra term. And UL times VH 2 to the n, that has to get it, that has to be removed. So those terms have to be taken care of. In fact, UH times VH, that's what I should have said, because we need the other terms in here. The H and L term products, like L and H, they're needed, but the other ones, UH and VH and UL and VL terms, are not needed. So all they had to do was to subtract those two terms in here from the total. Well, in the subtraction, they use UH and VH and UL and VL, but they computed them here once, so that's recycled. And the last term, which is this term, has also been computed. So the terms that you need, product terms, are UH and VH, UL and VL, second multiplication you have to perform, and UH plus UL times VL plus VH. That's all you need, because these terms that are also used here are already generated when in fact you multiplied UH by VH, which is the same thing as here, and when you multiplied UL by VL, and that's the same thing as it is here. So you got those in there, and therefore 3 multiplications are required. So I don't know how this term actually got in here, because this doesn't seem to be what I intended to write down here. Maybe I should just delete this here. That's not something that I think this just stayed in there. This is not. This is just basically what we had out of the Wallace multiplier, so that kind of goes away. But there is a recursion that we could actually use that to express this, which is, I think, probably done on the next page. This next page basically shows how this multiplication is performed. So you could see that the term that we multiplied here, UH plus UL times VL plus VH. By the way, these additions have to be performed for us to be able to do this. They lined up here because they are shifted by 2 to the n, as you can see. And UH and VH, of course, is shifted by 2 times 2 to the n, and so it's still shifted to the left. And UL and VL is not shifted at all. And UH and VH plus UL and VL is also shifted by 2 to the n. This will be subtracted, so we need a subtractor at this point. So in this example, we really take a 4-bit number, which is like U, and a 4-bit number, which is like V, and perform the multiplication by creating the higher and the lower portions of U and V, and then writing this term out, and there's a subtraction to be performed, which is basically this last term. So if you just do the additions and then subtraction, you just get yourself a product. So here's the actual formula that will just represent what Karatsuba-Ofman algorithm will generate. And you can see that that the Tn, the time of computing, this should have been 2n, but we could just still assume that we just replace 2n by n, and then of course n itself becomes n over 2. When you do this recursion, you get yourself this solution, which is easy to show, and I'm going to skip that. And so it gives you n raised to 1.585. Now this doesn't look like it is anything that is impressive, but this is a sequential multiplication. That is to say, in the case that we do things serially and go back to the very first multiplication steps we performed, that would have taken order n squared, because we had this m cycles, which would be in this case equal to n of addition, each of which would take n time, because we're using maybe a ripple adder. So that would be order n squared. But this is now order n raised to 1.585. As you can see, this is kind of like reducing that time. Of course, if you use a Brent and Kung adder, as we would do at this point in time, and this, I have to say that when Karatsuba-Ofman actually invented this algorithm, that was in the 1960s, Brent and Kung introduced their adder into the literature in late 70s, early 80s, let's say. And so the time difference is kind of like revealed here, because Karatsuba and Ofman probably would not have done this in a way if in fact they knew that could be done. That is, the adder addition step can be simplified. Now, it has to be stated also that there were some fast adder circuits back then, but they were not algorithmically proven to be order log n delay. But if you use the ripple adder, this certainly beats the product of that sort, which would be order n squared, and so it cuts it down. And not only that, but people have built on this Karatsuba-Ofman multiplication algorithm to come up with simpler, not simpler, but reduce this quantity down to like 1.37 or so. So they've been ever since their discovery, the Karatsuba-Ofman discovery, they've been trying to basically reduce this, bring it as close as possible to something like order n, which would be effectively like ripple addition time before multiplication. It's tough, but people have been trying. So, but you can also use this Karatsuba-Ofman algorithm for addition, for in parallel, to reduce the time, to avoid the addition problem. So this is how you would do it in parallel. Instead of like doing these 3 steps, the 3 additions is what, not 3 additions, 3 multiplication steps we talked about here, like 1 multiplication, a second multiplication, and the third multiplication. Instead of doing them one at a time, you can actually do them all at once. This is what this algorithm is basically indicating. 3 things are done in parallel. If you did this in parallel, then the time, basically all of a sudden the 3 goes away, and then if you replace the addition by log n, you get yourself an ordered log square n addition multiplication time, which is still not as maybe impressive as Wallace's answer, but at this point in time you could see that we are kind of approaching that, because that will be log n, this is log square n, and this is a parallel algorithm as opposed to a sequential algorithm. And finally, let me just say this, the best known result, actually, I guess something that is practical in some sense. Even this is not very practical compared to Wallace or Karatsuba-Ofman. It would be the one that is discovered by Schoeninger and Strassen, German scientists, which give you order n log n log log n. This is again sequential algorithm compared to Karatsuba-Ofman's n1 raised to 1 plus epsilon kind of a result, which certainly supersedes this or surpasses this in complexity. And they use a fast Fourier transform. Now, this algorithm was also, I think it was improved by a person, I think whose last name is Führer, but it is not as, I guess, in terms of the numbers that you have to consider for that the Führer algorithm will only surpass would do better than Schoeninger and Strassen if you take numbers to be very large, like 10 to the maybe hundreds or some very large number, maybe more than 100, maybe 1,000 or so. So numbers that are completely beyond the realm of the numbers that we use with all the encryption and other techniques today. So, you know, this is just a brief, I guess, exposure of the class to the ideas of multiplication. You know, just to recap, we began with sequential multiplication, and we talked about recoding, and then we talked about sign multiplication, and then we talked about how to speed it up by way of recoding helped us a little bit with to avoid shifts with ones or the one multiplications by just simply eliminating trains of ones in the multiplier operand. And then, of course, the Wallace multiplier really help us reduce the time to log n. But the base of the logarithm is 3/2, the one we did in class here in the video, also partly in class. And then finally, we talked about Karatsuba-Ofman as another technique, and then finally Schoeninger and Strassen. I didn't really talk about it. This requires a lot of energy and time to cover, and probably properly belongs to a graduate class in computer science. So, you know, if you're inclined to go in that direction, I'm sure that you will be taught this. But for us, just to have this knowledge, of course, is sufficient. You can read up more about this if you feel like it. The critical thing was that, you know, we kind of covered, we talked about high-speed multiplication at the beginning of the class. So this sort of like brings it to that point. So with this, let me just bring this video lecture to an end. And if my time permits, I'm going to talk about division also on video, and then I want to cover floating point operations maybe this week in class. But until I see you tomorrow, have a great evening.